All right, hello. So, I'm going to talk about this thing. This thing here is Parker Solar Probe. Parker Solar Probe has touched the sun. It has scooped up pieces of the very outer layer of the sun and allowed humanity to measure it for the very first time. Okay, why even bother trying to touch the sun? First of all, this is a thing humans have been imagining forever, right? Everybody's familiar with Icarus and the idea that, you try to reach the sun means to try to get to some impossible object, right? Or maybe you've seen this version of Icarus, right? Anyway, whatever. Okay, so why else do we want to do this? Another reason why we want to try to get to the sun is we want to understand it. The sun impacts everything that happens on Earth, right? The source of life on Earth. The sun is our energy source for the vast majority of life on the surface. Also, this, if you get a moment to read it, I'm just going to kind of summarize it. This is from the Rocky Mountain News. Right, this is the sun touching Boulder directly. And this is from 1859, one of the first editions of the Rocky Mountain News, which of course has since closed, but whatever. Point is, there were a bunch of miners right here in Boulder County, and they were woken up in the middle of the night by an aurora so bright. That means the sky lit up so bright they thought it was the middle of the day. What this was, and what was determined later, this is what's known as a solar storm. This is a piece of the outer atmosphere of the sun that gets ejected from the sun and strikes the Earth's magnetic field. When that happens, those particles can end up in our atmosphere and cause it to light up. So this was something right here in Boulder, right? When this happened, this was a thing called a white light flare that was observed. This means an incredibly bright flash and huge release of energy on the sun. And the point is that they determined that this affects Earth. What happens on the sun affects what happens on Earth. And in this case, in 1859, there were some long conductors, telegraphs. And what happened? Some of them worked without power. Some of them burst into flame. Some of them stopped working entirely. Okay, that's what we had in 1859. What long conductors do we have right now? Maybe our entire power grid. Maybe every oil and water pipeline across the world. These are long conductors. When our atmosphere gets full of these charged particles and conducts currents, those currents end up in those long conductors that humans have built and caused trouble. Therefore, we want to know how the sun behaves. This, I got all screwed up, whatever. Anyway, this is something that's called space weather. And it's the idea that things that happen in space impact what happens on Earth on human timescales, like on days, months, hours, those kind of timescales. And these kind of space weather events are things that start at the sun. They can mess with telecommunications, our aircraft and satellite systems, our power grid, and our GPS. Can you play this? Do you have the ability to do that? And we can see this from right in Boulder. This is from Lyons, right, looking north, and what you're seeing are the aurora. This is an image taken, or a video taken in May, just of last year. So this is still happening. The sun is always doing this. And occasionally, those bursts of energy from the sun are strong enough that they affect the atmosphere all the way down to Boulder. So in May of 24, we got some bright lights. In 1859, it was so bright they thought it was the middle of the day. All right, why else go to the sun? Stars we can get to. Stars we cannot. Right? All right, sorry, astronomers. That's where we're at. There's one star we can reach. So if we can go there and explore that, maybe we can learn something about all the rest of the universe that we cannot get to. Okay, so what do we know about the sun? We know that the sun is a plasma. Oh, what the hell's a plasma? So a plasma is a gas that gets so hot that the atoms come apart. The electrons and the ions fly apart, and they generally stay apart in a space plasma. You might know other plasmas like neon signs, lightning strikes, and plasma welders or TIG cutters. They have the same kind of effect. We also know that the sun is magnetic, just like every other star. Okay, I had fridge magnets, so clearly you know what a magnet is. So what we wanted to understand, there's the many things that we do not know about the sun. One is what part of the sun creates that solar wind, that outflow of particles that impacts the Earth? We don't know that. Why is the solar wind so fast? It moves incredibly fast, 400 kilometers a second. I don't have the conversion to miles per hour. It's really fast. Why is the solar wind so hot? Of course, the sun is hot, right? But when you expand a gas, it should cool off. But the sun's gas, as it expands, does not cool off in the way other gases do. It stays hot. Why? And then finally, because the things that happen on the sun affect the things that happen on the earth, can we predict the solar wind? These are all reasons why we want to go close to the sun. Can we answer these questions? How do we do it? We get close. How do we get close? With this thing. So this is a spacecraft called Parker Solar Probe, and it is designed to get closer to the sun than anything ever. How close did we get? We got down to the 4-yard line. So if we consider Earth, out here at 215 solar radii, we got closer than Venus. We got closer than Mercury. We went all the way into here. This is 2 scale. All right, so the solar probe got within 9 and a bit solar radii from the center of the sun, so 8 and a bit from the surface. We're actually down there scooping up the outer layers of the sun to measure them. This is the spacecraft. This is it getting built. Solar probe has this really special heat shield that keeps it alive. If the spacecraft tilts more than a degree, it melts. So they have to keep it pointed at the sun all the time. You can see it's not very big, right? Here's some people standing next to it, so you can see it would fit in this tent easily. You could stand it up. So not a large spacecraft. Can you play this one? This is just a cartoon of Solar Probe. It launched in 2018. So this thing has been up, approaching the sun, getting closer and closer for many years. The closest approach happened just on Christmas Eve 2024. Which is not so long ago. So we're just now getting some of the best data from the mission back, where we just got as close to the sun as we're ever going to get. Okay, so what did we learn? We've been up there since 2018. Did we learn anything useful? Yes. We learned, for example, that the magnetic field of the sun is structured as these switchback structures, right? So we all go hiking. We live in Colorado. Come on. So you all must know what a switchback is. It's basically something like this, a jog in the field. And it turns out that the solar wind is full of those things, and they may be related to the acceleration of the wind. We found that one source of the solar wind is related to where these switchback structures come from. There's an imager, or a camera on Solar Probe, in addition to measuring the plasma that this probe flies through. And we've actually watched a solar storm, which is one of those things that cause the aurora, blow away part of the interplanetary dust cloud, which was a totally unexpected observation, so that's been kind of fun. And then finally, in this last orbit, we did fully cross into the corona. So we got into the part of the solar wind that before it's fully accelerated, so right near the surface. Okay, so what about our big questions? Did we solve these? Yeah, okay, like Margaret said, science, you do it one step at a time. So, did we solve what part of the sun creates the solar wind? Sort of. We found some regions where more specific types of solar winds seem to originate from. So did we solve the whole problem? No. Part of it? Yes. Why is the solar wind so fast? That we actually did solve a big chunk of. And it's related to the idea that electrons are lighter than protons, and so they can more easily escape the sun and drag protons with them. Did we figure out why the solar wind is still hot? No. But we got some more ideas, and we've been able to take the list of ideas and to cross off many of them. So we're narrowing down the possibilities. And can we predict the solar wind? With the basic information on the physics of the solar wind we're getting from Solar Probe, we're getting better at it every day. So that's my message to you all. Keep exploring, keep these amazing missions going, so we explore these parts of our solar system and our world that we've never been to. Thanks.
Malaspina now. Yeah. Is it a one-way trip, or can it escape the gravitational influence of the sun?
Solar Probe is never coming back. And in fact, it's actually very poetic. Because what will happen is at some point that thing will run out of fuel. And when it runs out of fuel, it can no longer point the heat shield toward the sun. And so what will happen is the spacecraft will, first it'll melt, and then it'll turn to a gas, and then it will turn to a plasma, and it will get blown out and become the solar wind. first thing to do to get involved is to call your Congress people, representatives, and tell them not to zero out the funding. But right after you do that, come talk to me.
All right, any more questions? Yes. Aurora down here, and I'm watching the values on solar weather forecasting sites. What's the combination of parameters I should be looking for?
So there's an easier way to do that. You can do what you're saying. There are websites that'll give you the sort of intensity predicted for solar storms. The Space Weather Prediction Center, for example, tells you that. But there's another website out there called Aurorasaurus, and this is a citizen science initiative, and I highly recommend that you go check that out. And what it is people basically go outside and look for the aurora, and whenever they find it, they snap a picture on their phone and upload it to this site, and you can see in real time where the aurora is. So I would recommend Aurorasaurus, but if you're going to go look at the Space Weather Prediction Center, they have a G classification, so they have G1 through G5, and I would just look for that classification. If it's 3 and above, you're probably going to get a pretty good storm.
We have one question here too.
What material is the shield made out of to withstand that kind of heat?
Okay, so that's a great question. The heat shield itself is made of a carbon foam. So imagine taking like pencil lead and making it a foam and then making it, a foot thick. That's basically what it is, with a white paint cover on the front. But bits of the spacecraft, these antennas, for example, that's the instrument that I work on and that we built a part of here at University of Colorado. That thing has to be exposed to sunlight to survive. So that's made out of niobium, which, if you've heard of tungsten, that goes inside light bulbs, it's then that same kind of element where you can heat it to ridiculous temperatures and it just glows instead of melting. But it does get about 2,000 degrees C at the front of the heat shield, so it's very, very hot.
All right, we have time for one more question.
Would any glowing affect the data that you're gathering?
Yeah, it totally does, actually. So this camera right here that saw that solar storm blow out some of the dust, that camera is positioned, and these antennas are positioned because these things glow. They get red hot, literally, and then they glow in the visible part of the spectrum. And this is a visible light camera. So they had to design the whole spacecraft so those two interfered with each other as little as possible. So yeah, the whole thing glows.
All right, let's give it up for Dr. Malaspina. All right, and now I want a round of applause for yourselves because we have sold out the Nebulita even before the event even started. So congratulations, everybody. Thank you for buying that.